So before we jump into sizing guidelines for structural steel elements, I wanted to talk to you all just a little bit about structural detailing. This topic is very important, not only because there may be questions regarding structural detailing on your ARE, but it will help you to understand how a structural engineer designs their details. Often in practice, structural engineers and architects will cut the same sections and detail views in their BIM models to define the respective scopes of work in that area. The architect will sketch in the structural engineer's detail components and create a note that says, "Refer to structural." Likewise, the structural engineer will sketch in architectural elements and add a note that says, "Refer to architectural." Occasionally, you will find that these elements that they refer to do not match up. Of course, when these uncoordinated drawings are turned over to the contractor, it typically generates an RFI, or a request for information, which could ultimately delay the project. So it's important that architects and engineers have a basic understanding of the goals they are each trying to achieve with their details. Another reason why this topic is so important is because, with steel design especially, the greatest design challenges are often in the connections. Since steel is a one-way system, the load has only one direction it can travel. As we've mentioned before, in a typical steel bay, load travels from the deck to the beams, to the girders, to the columns. And so ideally with a steel building, we have these perfectly rectangular grids where all of our columns end up in a line. But what happens if the architect wants to place a corridor that would lead into these columns, like this? Well, in that case, they may direct the structural engineer to move these two columns over, as shown on the right. So let's look at what happens to our load path now. So let's place a load in the middle of this bay here. Half the load will travel to the beam above, and the other half will travel to the beam below. Once in the beams, half the load will travel to the left, and half the load will travel to the right. The load that travels to the left now has a direct path to the columns in the corner, which is ideal for structural detailing. However, the load that travels to the right, you can see that half will travel down the girder to this column directly, which is good, but the half that travels up the girder now transfers into another girder. And it's that extra step that creates complications, as now we need a larger connection between these two girders. Whereas before we could place a large connection simply into our columns, which are long vertical elements anyway. And so we have plenty of room to create a deeper, stronger connection. Additionally, you can see down below here I have added this slanted beam. And here you can see that these angles are not 90 degrees. Ideally, with structural connections, we want to keep our angle at 90 degrees, as this makes welding elements much simpler. Connecting to an angled beam like this creates a skewed connection, which can also add cost to the project. Finally, you can see this bay in the bottom right corner. I have the deck span turned another direction. This design decision may be due to pieces of equipment that are in this room, or simply because the architect wished to have shallower beams in this area. Accommodating for these design criteria can be done with steel, of course. However, it creates complications in the connection of the deck and in the detailing between these two perpendicular deck spans. So, in summary, we must always be conscious of the load path with structural steel. All loads must eventually have a path to the foundation. The more direct that path, the more efficient the structure, as we've mentioned before. With structural steel, it's especially important to keep load path in mind, as steel systems are one way. When we talk about concrete later on, we will see different two-way systems that can accommodate for greater flexibility in arrangement of columns. But for steel design, irregular floor layouts can drive up cost because, with steel, the greatest design challenges are typically the connections. Unfortunately, in my personal experience, I have found that most colleges don't spend a whole lot of time discussing detailing. In fact, even most structural engineering undergrad curriculums don't cover structural steel connections, which means that this content you're about to learn will actually put you a step ahead of many young engineering professionals. So, the first step toward understanding a structural steel detail is how to read this type of symbol, a weld symbol. And I posted a resource on Moodle that summarizes the most common types of welds, and in this video I'm going to walk you through what each of them mean and how we might use them. So let's dive into this, starting with the different elements of a weld symbol. So, moving from right to left, you can see we start with an arrow, and that arrow obviously points to where the weld will be applied. Moving to the left, you can see that we have this field weld symbol, this flag. This flag is critical because it calls out to the contractor which welds will need to be done in the field. Field welding is, of course, more costly than welding in a shop for a variety of reasons. First and foremost, when you're welding in a shop, there are no environmental effects. Especially up here in Boston, we have to be conscious of the fact that it gets very, very cold outside, and when it gets very, very cold, welding becomes much more tricky. And so as much as possible, we want to make our welds done in the shop as opposed to done in the field. Also, when we weld in the shop, it means that the element can be laid out on the ground and easily accessible for the welder. However, when welding in the field, that element will often already be erected and already put into place, and so we will have to send someone up to that location where the weld needs to be done, which obviously can get tricky. So again, as much as possible, we want to minimize the number of field welds that we do in a project. However, there are some very good reasons for when we do want to use field welding. For example, if it's something that needs adjustment in the field or something that needs coordination. Moving again to the left past the flag, this is where we have all of the elements that define the size and shape of the weld. Starting with the length of the weld and the pitch. So if the weld has a specific length that needs to be defined, it will be placed furthest to the right of all the numbers on this line. And that's regardless of whether this reference arrow is pointing this way or pointing this way. The length will always be on the right side, and the size will always be on the left side. Next we have the actual symbols. So here is where we are going to place the symbol that defines the shape of the weld, whether it's a fillet weld, a square weld, a curved type of weld, etc. Those symbols will go here. And as I just mentioned, the size of the weld will be placed on the left side. And lastly, we may occasionally have this open pair of brackets here, and this is where the structural engineer will write any particular notes they want to include. For example, they may write typical unless noted otherwise, or they may say top and bottom, etc. Those notes would be placed behind these brackets. So this drawing on the left is a bit complicated. It shows every little piece of a weld symbol if you really want to dive into it, but the really important stuff you need to remember is this field weld symbol, the symbols for the shapes of the weld, the length goes here, the size goes there, and lastly the tail, where the structural engineer places any specific notes. Before we jump into defining the different types of shapes of welds, it's important to note here that if we place that shape symbol below this line, then that will be telling the contractor that the weld is to be applied on the same side as the arrow is pointing. Whereas if they place it above, then that means that the contractor should be welding on the opposite side. Now, let's look at some basic symbols for types of welds. Of course, the most popular is the fillet weld. And a fillet weld looks exactly like the symbol, and that's more or less true for the rest of these symbols as well. Fillet welds are typically used for joining two perpendicular surfaces, as you can see below. They're useful because they typically don't require you to cut or modify the actual steel element, as opposed to a groove or a butt weld where we are typically cutting out a piece of steel and filling it in with weld. So this would be an example of a bevel weld, as opposed to a fillet weld that would look like that. So we'll go a little more in depth with these different shapes down below in just a moment. For now, let's reiterate what we learned above about the placement of these symbols. So, here we can see that the symbol is placed below the line, and so that means that the weld will be applied on the same surface as the arrow. Next we have the symbol moved above the line, and so that means that the weld will be applied on the opposite side. And finally, if we have the symbol on both sides, of course that means that we will place the weld on both sides as well. Now here we have a weld that has a defined size and length, and the shape is again a fillet weld. So what does this 1/4 inch refer to? So if we draw the shape of our weld, it's a fillet weld, so it'll be triangular. The 1/4 inch refers to the vertical and horizontal legs of this triangle. So that will be 1/4 inch. Next we have the 6-inch dimension, which refers to the length of the weld. So the length along this member will be 6 inches. So all of this will be weld. It's also important to note with weld symbols that we never place the dashes to indicate inches. It's just understood that these numbers are given in inches. So we can remove those dash marks to simplify our detail. Now what if we removed this 6-inch dimension? What would the length of the weld be in the field? Well, if we don't place any number here to define the length of the weld, then it's understood that the weld will be applied to the full length that these two elements are attached. So the contractor would have their welder fill in the weld like that. Now let's briefly look at some other types of welds. And actually, with the exception of the plug or slot weld here on the bottom, all of these are groove or butt welds. Starting with the square weld here. So this is when we have two parallel pieces that we're joining together, and we have just a simple square weld between the two. The tricky part with this weld, of course, is that you have an open slot between these two elements for the weld to simply pass through. And we'll talk about how a welder would prevent their weld from simply dripping through these two elements in just a moment. When joining parallel elements, it's often actually preferred to use some type of V-weld, and there are several different configurations that are given here. or perhaps a bevel weld. Next we have the U weld, or a J weld, and after that we have flare welds. So we have flare V and flare bevel weld. These type of flare welds can often be pretty expensive. So you can imagine welding round to round is not very ideal, or even welding round to straight. So finally here we have the V with a bead weld underneath, and a V weld with a backing bar. And this backing bar and the bead weld here are means of preventing the weld from simply dripping through the two elements, as I mentioned before. So the welder would come in and simply apply a small tack weld to the side of this backing bar, and then they would fill in the weld here. And the backing bar would prevent the larger weld from dripping through the elements. And the same goes for this small bead weld above. That bead would be applied first, and then the larger weld would be filled in after. Okay, so let's continue on to looking at a typical moment connection. So this would be a typical detail that would show up on a project that has moment frames. We have our beam connecting into our column here, and of course you can see that we're connecting in the strong axis direction to achieve the maximum amount of strength from the column. And of course we are transferring both a shear force here as well as some kind of bending moment. And as we've mentioned previously, it's the web of the element that controls the shear, and so we're going to pass the shear force through an element that's connected to the web of the member. We actually call this typically a shear tab. And it's the flanges of the beam that control the bending stress. And so to transfer that bending stress into the column, we need to connect the flanges of the beam. And we do so with these bevel welds. So we trim out a portion of the beam, and then we apply a backing bar underneath where we are going to apply the weld. And then after those backing bars are put into place, we fill in this bevel weld. And of course that type of connection would have to be done in the field, because we can't ship the column with an entire beam attached to it. However, we can ship the column with this small shear tab applied to it. And so this weld does not need to be a field weld. This tab would have a weld applied to it in the shop, and the column would show up with this little plate sticking out of it with holes in it for the bolts. And so this is what that connection would look like in 3 dimensions.